Start the second session. I will chair it, and we have four talks. And first talk will be Eduard Gorbar from Kyiv.
I would like hello. I would like to present you our work done on viscoelastic tensor and hydrodynamics of altermagnets. This work was done in collaboration with Arsen Gerasimchuk and Pavlo Sukhachov, as well as I included in the final part of my talk our joint work done with Trondheim Group. And I will talk later about this. Okay, first of all, I would like to talk about the motivation. So, main motivation of this work was connected with the question whether momentum-dependent spin splitting in altermagnets could result in non-trivial interplay of spin and electric flows in the hydrodynamic regime. And related to this question, another question, if this hydro regime is realized in altermagnets, what will be features and peculiarity of the hydro regime in altermagnets? I would like also to say that this work has obvious weakness as the hydrodynamic regime was not experimentally observed in altermagnets. So at present, it has only theoretical character. Okay, so let me remind you about the relation between ohmic and hydrodynamic regimes. Actually, the story is a tale of two scales. One scale is given by momentum relaxing and another momentum conserving length. So here is a schematic picture of ohmic regime. So what we can see here. So we have our electrons and impurities. And according in the ohmic regime, what we have, electrons actually interact more strongly with impurities. So electron impurities scattering dominates over electron and electron interaction. And so this regime where momentum relaxing length is smaller than momentum conserving length. In the 60s of the last century, it was found by Gurdjieff that another regime is possible where momentum conserving length connected with electron-electron interaction is smaller than momentum relaxing terms. So in this regime, what we actually have, we have impurities, but this dense number of electrons means that electrons strongly interact, so they kind of bound together and form a fluid. Okay. So this hydrodynamic regime, for example, let me show how it actually works and why it produces different responses connected to the ohmic regime. For example, let's consider this is experimental work done with hydrodynamic flow in graphene. So what we can see here. So there is a constriction in graphene, and here the electric potential is plotted, and the electrons streamlines. So we really see that in these contradictions, streamlines are more dense. So what then the consequences of this situation? Here, current density is plotted with respect to the length of this constriction. And what we see, in the ballistic regime, we have this blue line, and in the hydrodynamic regime, we have a classical Poiseuille profile. So it's kind of parabolic shape. And what is interesting that here resistance is plotted with respect to temperature. And this is again real experimental data in graphene. What we see, this is for different, for three values of electron density. Let's concentrate on, for example, the upper one. So the solid black line shows resistance in the ohmic regime, and here black dots display experimental results, and dashed line shows hydrodynamic results of hydrodynamic simulation. So definitely what happened, why it's called higher than ballistic flow, that resistance in the hydrodynamic regime could be smaller than even ballistic. So how it can be explained? It's actually easy to see. For example, if we have somewhere constriction, here electrons bump into walls more frequently than in this regime, where they can go through together. Okay, so again, just simple reminder to you, hydrodynamic variables. So hydrodynamics is the macroscopic theory which studies the motion of fluids. We have fluid velocity, we have particle density and pressure. And actually hydrodynamics is based on the conservation law of momentum, mass, and energy. And key equation are, I believe, familiar to you. This is the Navier-Stokes equation. This is time derivative with respect of velocity. This is convection term. This is actually, this term makes hydrodynamic equation quite difficult to solve because this term is non-linear. And then we have gradient of pressure, diffusion term, eta is viscosity, zeta is bulk viscosity, and this term describes diffusion, and the last term compressibility. How it works, if we have shear stress, this diffusion terms defines profile of velocity in this case, in this channel geometry. And in addition to the Navier-Stokes equation, we have continuum equation. So it's quite familiar form, and I think there is no need to talk about this. And in this regime, the electric current is given by product of electron density times velocity. Okay. Hydrodynamic regime experimentally was observed in gallium arsenide, graphene, and wild semi-metal wolfram phosphorus 2. Okay. Now I go to altermagnets, and here, for example, I would like to show experimental realization of altermagnets in manganese telluride and more complicated compound. And it was given this is actually last year work, and this work, this year work. And in our work, we consider the simplest model of altermagnets, D-wave altermagnet in 2 dimensions. Hamiltonian is quite simple. You see, its energy dispersion is absolutely clear from here, because this is the third Pauli matrix. So for spin up, we have plus here. For spin down, we have minus here. And this is clear. This Hamiltonian is quadratic. So what we have, according to the standard mathematics, just ellipses. one, and here I plotted for T1 not equal 0 the Fermi surface, and clearly here we easily see a splitting of, for example, if T0 is 0, then we would have just a circle, right? And for example, if T2 is not equal 0, it's the same picture, just rotated. So there is an interplay, actually rotation related to these two parameters, T1 and T0. And last term, of course, is chemical potential. And first, we try to to calculate viscosity by using the Kuba approach. Let me remind you maybe a few words about stress and viscosity. For example, let's consider the, for illustration, Kelvin-Voigt model. So we have here stress and then strain. And this is derivative strain rate. So this is derivative of strain with respect to time. Eta is viscosity. Actually, you see why it's so. Let me remind you this equation. And eta enters with u. With hydrodynamic velocity. So this is indeed this term in Kelvin-Voigt model. Eta, this coefficient is actually really viscosity. And this large E, this is the modulus of elasticity. So Kelvin-Voigt model, it actually kind of simulate response to stress where viscous and elastic forces. Okay, so then just definition, what is viscoelasticity tensor in D-wave applied to altermagnets. So we have this formula, standard expression in Kuba approach. And what we found, we looked for actually mostly for anisotropic contribution, and we see that it is not zero and related indeed to this spin splitting coefficient T1. But actually it's more clear in physical terms to proceed with hydrodynamics and the derivation of hydrodynamic equation in altermagnets is quite standard procedure. I mean, we applied standard procedure. So we'll begin with the Boltzmann equation. So in the relaxation time approximation, this collision integral clearly shows that we use the relaxation time approximation. Then we applied standard Holloway ansatz. So this is a distribution function. It has the Fermi-Dirac form, right? Where in the exponential there is an additional term related to hydrodynamic velocity. And then we calculated hydrodynamic equation, integrating over momenta, multiplying by momentum, integrating again, and multiplied it by energy, integrating again. So this is standard textbook procedure, and we end up with this equation. So I would like to bring your attention to this matrix T. Actually, you see, for example, if we don't have this spin splitting term T1 and T2, then this matrix is just proportional to the Kronecker symbol, right? And in this case here, this actually EG, this G takes two values, 1 and 2. This is actually orthogonal vectors in X and Y direction. And if these terms are absent, then we have standard Navier isotropic Navier-Stokes equation. But anisotropy is indeed present due to this due to contribution of these two spin splitting terms. And what are the results of this? We consider the simplest example. This is flow in the channel geometry. So what we clearly we applied the non-slip boundary condition. So definitely velocity cannot have normal component, but we also non-slip boundary condition means that there is no slip in the boundary. So tangential component is also given, is also zero, sorry. And then we have classical pose profile of current velocity. And analytic formula is quite simple. So it's linear in applied electric field. And this parameter L, this is famous Gauge length, which defines actually how strongly deviates from vertical line this profile. And what is interesting also that anisotropy due to spin splitting produces also Hall voltage. So you see we have Y component and it is indeed related to spin splitting coefficient T2. And if we ask me about the spin current, it is the same as this expression with replacement with multiplication by rho tilde over rho. And rho tilde is related to different density spin up and spin down electrons. And we also looked at the non-local response and considered two cases, contact on the same side and the opposite side. So in the case of...
you have a few minutes.
Okay, yeah. In this case, we got this picture. So what we can see here clearly here we have sink, and here we say we have source, and then we have I would like to draw your attention to vortices. Actually, we did not proceed further with this because this is absolutely the same picture as was calculated by Torre, Tomatin, Gain, and Polini. So we looked for non-zero values of T1 and T0. Picture practically stays the same. So no big change. So then we looked at the constant on opposite side. Here, actually, again, this upper panel picture is the same as in Falkovich and Levitov paper in graphene. So again, we have vortices. So let me remind you that vortices is actually like flagship of hydrodynamic regime. So it's because in the ohmic regime, we don't have vortices. So it's again the same. So I did not show here a picture with for spin, but we see, for example, this spin splitting coefficient, its effect actually related to the modification of the central part of this picture. And also, I would like to draw your actually attention, maybe you are not familiar. For example, here, we have here positive electric potential and also here negative contribution. This is again a feature of the hydrodynamic regime. It's impossible in the ohmic regime. And actually, we also motivated by our results in the hydrodynamic regime to look at the ohmic transport regime. And this is just 2 minutes I wish to say about our work. Actually, this work was done by me, Gerasimchuk, Sukhachev, and our Trondheim colleague Kohlberg, Hoth, and Linder. Actually, this paper appeared just today in the archive. In the hydrodynamic regime, spin up and spin down electrons have the same drift velocity, and in the ohmic regime, spin up and spin down electron motion is no longer coupled by strong electron-electron interaction. Then we solved this equation for current in this regime, and our result as following. So in the case of contacts on opposite sides, electric current streamlines looks quite familiar to the ohmic regime. So here you see, for example, close to sink, there is no green areas, and similarly close to the source area, there is no red areas. But what is interesting that due to spin splitting coefficient T2, or in the case of spin current, we observe spin vortices even in the ohmic regime. And actually, we did for contact on the same side and observe similar pictures. So nothing special in the electric current. And again, we definitely see vortices in the spin current. Actually, if we inject spin current, what we also found that if we inject spin current, for example, due to spin Hall effect, we will have also electric vortices in the ohmic regime, even in the ohmic regime. Okay, so my summary. So to summarize, anisotropy of altermagnetic Fermi surfaces allows for additional terms in the viscoelasticity tensor and is really manifested in transport properties. In the channel geometry, the altermagnetic spin splitting leads to non-trivial spin density in spin current, and the spin current requires a Poisson profile for in the case of no slip boundary condition. Swirling spin currents could be realized in the ohmic regime due to altermagnetic atomic spin splitting. And hopefully the obtained result could provide signatures of the hydrodynamic transport regime in altermagnets. And also I think our results about the possibility of realization swirling electric and spin currents in the ohmic regime should be checked and maybe studied more. Thank you very much.
Thank you. Swirling, I missed, like turbulence.
No. I mean with vortices.
Do you expect turbulence regime?
No, but you know, turbulence regime is realized in at large Reynolds number.
Yeah.
And this means, but first, for example, laminar regime is related to just appearance of hydrodynamic regime. So turbulence could be realized in really quite clean hydrodynamic systems.
So I have a related question. Is there a critical value where, because you say there's no vortex in the
No, there is no critical.
No critical
No. Just you see how to say vorticity could be small. It's kind of continuous. It starts from
because there's a length scale related to it.
Yeah.
I see. Oh, that's super interesting that you have a vorticity in the spin current, but not any charge current. And do you understand?
But if we inject spin current, it will be just vice versa.
Yeah, of course. Then it must be right. But do you understand why this is in the ohmic regime and not in the hydrodynamic?
And actually, all this is related to this that this matrix is not again diagonal. It's actually maybe even more clear to understand. Like it's like here. Because this spin splitting part, they
Because you rotate a
they produce interplay between spin and electric. Exactly.
Sure.
Mm-hmm.
But physically, I'd like to understand, why this can happen in the ohmic regime, and does not happen in the hydrodynamic regime. And do you have a physical argument for that, or it's just questions?
No, but you see, in the hydrodynamic regime, in the hydrodynamic regime, spin up and spin down electrons have the same Drake velocity. So it's by definition.
You don't get out of it.
So in hydrodynamic regime, we have anisotropy.
The coupling.
We have anisotropy,
Yeah.
but in the ohmic regime, we definitely have this kind of separation of electric and spin currents.
Very nice.
More questions? Maybe online audience have questions on. Okay, one more question. Yeah.
Thank you. Do you expect some difference in macroscopically measured characteristics? Say, if you compare voltage ampere characteristics of altermagnet and normal metal, do you expect some measurable difference or not?
Yeah, I think so. Yeah, it should be. But first of all, we should realize hydrodynamic regime. And maybe it's actually more simple to look at the ohmic regime. Because unfortunately, as I already told, hydrodynamic regime, actually, I did not have time to speak. To realize the hydrodynamic regime, we could have ultra clean samples because impurities suppress. Because you saw that actually there is two scales, momentum relaxing and momentum conserving. And the impurities produces momentum relaxing, scattering. So we need very clean samples to realize the hydrodynamic regime. And unfortunately, at present, nobody knows.
But still, in the ohmic regime, you showed there is this whole effect. I think Cairo would
they
would not agree.
effects related to spin split and
This dissipative, so it's not maybe not called as whole, but that would be like a macroscopic signal.
Yeah, definitely. Yeah.
What sizes should have your samples?
Actually, I don't know exactly because we have some numbers, but actually, let me look and I will answer your question later. Just to be sure.
Okay, we should stop the talk.